So let's continue with part B. So it's ln x over x squared. Well, obviously we're going to do function evaluation to start with, so assuming that x is a big number. Ln of a big number tends to a bigger number, so we call it infinity. And the bottom is like a big number squared, that also tends to infinity. So this looks to us that this is an infinity over infinity type indeterminate form, and the L'Hopital's rule works perfect. We got to make sure that these two functions are differentiable for large x values. Well, the top function is an ln function, and we know that the only problem point for differentiability is 0, but we're very far away from 0 because x is a large number. And x squared is as well differentiable in fact, for all x. So regardless of whether the number is big or not, x squared is just differentiable. So why don't we go ahead and apply the L'Hopital's rule, saying that this limit is equivalent to the derivative of the top. So let me just write it clearly. So ln x prime divided by the derivative of the bottom. That's also x squared prime. All right, x squared prime. And we know how to take the derivatives of these functions. Okay, so this one has the derivative 1 over x. Okay, and the other one has the derivative 2x. Okay, at this moment, let's just stop and try to use some algebra before we pass the limit. So why don't we combine this ratio divided by 2x? So I'm going to put a 1 here, okay, and then I'm going to flip the bottom. So this will look like limit as x approaches infinity of 1 over x times 1 over 2x once you flip this. So that is in fact 1 over 2x squared. So now this is only one fraction, and I can pass the limit without a hassle, right? So as x approaches infinity, so 2x squared is going to approach infinity. 1 over infinity, or a huge number, is going to approach 0. As you see that, we started with an indeterminate form, infinity over infinity. And after the application of the L'Hopital's rule, we got this limit to be 0. Now for this function, there's no way to use algebra because we don't know how to factor ln function or any kind of algebra that would be applicable to this quotient to simplify. This example shows the power of the L'Hopital's rule in terms of handling an indeterminate form, which is in fact infinity over infinity. All right, here is the graphical outlook of ln x over x squared. Since the limit is as x approaches infinity, so I wanted to get my x min and x max to be large enough to see the behavior of the function. The behavior of the function around 0 is not a big deal because I'm not interested in that. So as you see that the range is kept in between -0, 0.01 and then 0.02. The blue curve sort of like tends to 0 for larger x's, but I wanted to double check what's going on for even larger x's. So I took my x max to be 10 to the power of 6, just to confirm that the corresponding function values get smaller and smaller, and in fact converge to 0. If you increase x in this direction, the corresponding function values get smaller and smaller, and they're now at the level of 10 to the minus 10. And as x gets larger and larger, you can confirm that the limit is 0. So again, graphical outlook of the function is always helpful to see the behavior of the function around the limit point. So once you have a chance to use your calculator for limit questions, you go ahead and use your graphing calculator just to see the behavior. And here is part C. I have the limit of x ln x as x approaches 0. Well, we can just do function evaluation right away. So as x approaches 0, well, this x is going to approach 0. And ln x, you can check the graph of ln x. When you get closer to 0, the function values tend to minus infinity. So this would be in the form of 0, something 0, close to 0 times a very large number negative or positive doesn't matter. So 0 times infinity is the same as 0 times negative infinity. So this is not 0 over 0 or infinity over infinity, which is what is stated in the L'Hopital's rule. So now I want to use some algebra to make this limit look like either 0 over 0 or infinity over infinity. So for that reason, why don't we rewrite this limit as ln x divided by 1 over x. Instead of x ln x, I wanted to rewrite this as ln x over 1 over x, because once you flip 1 over x, then that's x. You go back to the original form. But this way, when you pass the limit, so the top is going to be minus infinity. So this would be plus infinity. So then you run into the case of like infinity over infinity type indeterminate form. And now we are allowed to use the L'Hopital's rule for this top function and for this bottom function. So, and there's one-time application of the L'Hopital's rule. Let's be very specific here. So we take the derivative of the top and the derivative of the bottom. Okay. All right. So we know how to take the derivative of ln x. That's in fact 1 over x. So let me just write 1 over x here. That is divided by the derivative of 1 over x. But since 1 over x is x to the power of negative 1, we can use the power rule to conclude that the derivative of that is minus x to the power of negative 2. So we essentially use the power rule and put the power minus 1 down and subtract 1 from the power. Let me just write it here one more time. This is x to the power of minus 1. So we utilize the power rule. And I want to rewrite this term to see exactly what is going on in the bottom. So this is 1 over x divided by minus 1 over x squared. So at this moment, we should simplify this further, because I can flip the bottom over so that this limit becomes 1 over x times minus x squared over 1. Okay? So this is good news, because I can cancel out this x by the square here. So eventually, let me continue from here, that this limit is now reduced to the limit of minus x only, because in the bottom you only have 1. Okay? And we know how to find this limit because it's function evaluation. So as x approaches 0, minus 0 divided by 1 is going to be just 0. Originally, this was 0 times infinity type indeterminate form. After we used the L'Hopital rule by tweaking the given function and writing it as ln x over 1 over x, we got the limit to be 0. All right, here is the graphical outlook of x ln x. We're talking about the limit as x approaches 0. It should be from the right though, because otherwise ln function is not going to be defined. But as you see that, as you get closer to 0, the blue curve is in fact approaching 0. And just want to make sure that we're approaching 0 by zooming in a little bit more here. Okay, 10 to the minus 8. Then the corresponding values are getting smaller and smaller, as you see on the blue curve. These are the y values, right? They get smaller and smaller, and eventually they're going to converge to 0. All right, this ends the video. Thanks for watching. I'll see you in another video. Bye.